So hopefully you see something now that looks like something worth looking at. So yeah, I will, as advertised, talk a little bit about permeation testing. To start out, let's all get on the same page on permeability. What is it? First off, it's a quite important parameter for determining the transport of hydrogen through a material. It is actually the sum, or not the sum, it's the product of the diffusivity and the solubility. So what is done when you're testing to determine this is that you normally just have a disk of material that you then pressurize with hydrogen from one side, which is the upstream, and then you see how much goes through. And once you reach a steady state of flux, you use that data to determine your permeability. There is a little kicker in this, because when you're calculating the flux, then your fugacity of the activity of your gas, it will depend on the pressure, but it will also depend on whether it's a material or it's a polymer, and that is something to do with how the hydrogen can travel through the material, basically. But I think we will talk a little bit more about that, but essentially just means that when you look at permeability for a metal, it's not having the same unit as a polymer permeability, but then when you convert them into flux, you will have the same units, but then you will see the difference. Permeability varies depending on the material. Here is just metals, all shown at 293 degrees Kelvin, which is 20 degrees Celsius. And what we see here is that we have the iron has the highest, and then the 300 series, like IC 304 or 316 stainless steels are significantly lower, and then we have the oxygen-free copper as one of the even lower. An interesting point here, and the reason why I take it in here, is that we have something which is just a normal low alloyed steel, but we have a normalized 4130, and then we have the tempered and quenched 4130. And there is actually quite a difference between the two, which comes down to the crystal structure of it. The normalized is a ferrite and carbide, and the tempered and quenched is martensitic. So even we have a steel, which is, when we start out, it's the same steel, but we treat it differently. So even with the same chemical composition, we get different, mechanical performance. We also get different performance in terms of hydrogen. So all in all, the permeability depends on the surface effects, both area, what kind of metal it is, because that affects how well hydrogen will absorb to the surface before it can then dissociate and diffuse into the metal. We also have, of course, influence from the crystal lattice, the microstructure, and then we have all the imperfections, like Dieter was also talking about, dislocations and other things that will affect the diffusivity and solubility, and in some cases actually trapping the hydrogen inside the material. To talk a little bit about how we are testing hydrogen permeability on different materials. This is a simplified figure of our little test cell. And essentially, of course, like you will have to do when you have to consider using a specific material in hydrogen applications, we also have to consider what materials can we use to build this cell, what pressure transducers can actually maintain their position even though they are exposed to hydrogen. Some will be affected by the hydrogen building up even, and causing a drift. So we have this where we've taken into consideration the different requirements for materials, test durations, Also make sure that we had continuous data logging on both sides, both the inlet, outlet, simply to be able to really have all the data we need to be able to see if we see inconsistencies, or basically just to document what is happening and the conditions we're testing. The setup is quite flexible, so it's just 2 parts, and then in the middle we put our sample. One thing we use it for is to determine the charge time. Charging can be done with electrochemical or with gas, as Dida has been talking about. And the reason why we want to determine the charge time is because one thing is to look up in the literature and see how fast does something permeate through, but another thing is to see on the actual component you have, and that's what we are using it for, among other things at this point, is to see how fast, how long does it need to charge before we can subject it to other tests. And yeah, it basically gives you the ability to, or the possibility to investigate different effects on permeability. That can be coatings, or it can be just simple like heat treatments or mechanical working on different metals. One thing we took into consideration when designing this is to create as small a volume as possible where we need to have the gas, because with a small volume, we can test with higher pressures without it being too dangerous. And when you like, the more safety you need, the more costly things get, basically. Yeah, so I've already been sort of touching on this, but we do this because we want to do the right kind of testing for the purpose. So literature commonly use polished or at least grinded surfaces. You would often see palladium coating to increase the absorption, which is good when you just want to measure the permeability. But yeah, it's good if you just want to characterize your material. But in our case, we often want to see how does it actually work in a function. Now, what is the fitness for purpose? So of course, as is also mentioned in electrochemical standards, we want to, sometimes you want to take the surface that is going to be in your application, and that way you have all the effects from the specific surface geometry or whatever. It can also be, for example, it wouldn't really make sense to palladium coat the inside of something that you would never palladium coat and then say like, okay, we charge it for 2 weeks and that's enough to reach the steady state, but we can't palladium coat the actual component. So in reality, we would need a much longer period of time, in some cases at least, to be able to say like we have actually reached the steady state, we have saturated the material with the amount of hydrogen we can, we have made it as sort of brittle as possible. So that's one of our main purposes of this, and that's why it's a good one to use if you actually want to test components in your service conditions. Another thing Dida also briefly touched upon is that you can do this, you can do the charging electrochemically or by gas. And what we have previously had success with was to look at how can we use gas instead of, or how can we use an electrolyte instead of gas to reach the same amount of hydrogen in our material. And again, if we do manage to find this correlation for the hydrogen gas and can use that to create a more safe and more cost-effective way to test under really high pressure conditions. And it will of course also allow us to not only test in both ways, or not only charge in both ways, but also select the method that is most suitable for the specific case. So it's very, very short about what we're doing with permeation testing, some of the thoughts we've done about it, and what we would like to do in the future. Yeah, keeping it short.